our third sorting algorithm, insertion sort, 8.1. Yeah. This one, pretty easy. Yeah. Yeah. The idea, the implementation, pretty easy, but it's an interesting sorting algorithm. Yeah. Yeah. All right, so let's look at the idea. Yeah. Yeah, so the same sorting problem, we revisit. Yeah. The strategy here. Yeah. When we start Module 4, the topic is divide and conquer. So here we want to use divide and conquer to, to solve the problem. Yeah. And before we, because at this point we do not have any experience about divide and conquer, right? So we need to get some experience. So to get experience, start with the simple case. Yeah. When we start, let's do sorting, number of elements here, and n is a small number. Yeah. So let's start with very small n number case. Yeah. All right. Then we grow the data size one by one. Every time we increase the data size by one. Yeah. And see how much work we need to add. Yeah. Yeah. Because the previous sorting already completed. So we have that solution. So now after we add a new element, how to get the whole array sorted. Yeah. That's the basic idea. Yeah. All right. Yeah. So here you can see we increase the size by one. Yeah. Increase the size. So opposite divide and conquer, right? We reduce the size. Here we increase the size. Opposite divide and conquer. Yeah. But, essentially the same. Idea the same. Yeah. If you look at from the backward view, then it's a divide and conquer. Yeah. All right. Yeah. How to connect two adjacent cases. Yeah. Remember the gap. Yeah. Every time. Yeah. So in our module 3, recursive algorithms, we had experience. So we work on a smaller problem size, then larger problem size. We want to look at the gap between these two problem sizes. Yeah. Here, similar. Yeah. The difference, the gap. All right. Yeah. Intuition. Yeah. First, when we work on simple sorting, let's just use our intuition. Yeah. The first simplest case, one element array. Yeah, here, one element array. Then do nothing, right? It's already sorted. It's done with zero comparison. You get it sorted, okay? Yeah. All right. After that, we add a new element. Then one comparison. Yeah, should be enough. Okay? Yeah, one comparison. Yeah. Could be greater than A0, could be less than A0. Yeah, two cases. Yeah. So after one comparison, we get it sorted. Yeah. Here we just assume A0 less than A1, yeah, without loss of generality. Yeah. All right. Then next one, A2 element. Yeah. But when we want to work on the gap, the difference, A2, we bring it in. This current array is already sorted, ascending order. So that's our assumption. So we want to add a new element in that sorted array. So then the question, how much work we need to do to get the new element inserted at the right place? Okay? Yeah. Worst case 2, right? The best case 1 is enough, right? Yeah. So you have best case, worst case. Yeah. You have several cases. Okay? Yeah. All right. So now, from the diagram, it looks like an insertion operation, right? Yeah. Yeah. Current array in ascending order, the new element should be inserted somewhere, yeah, in the existing ascending order array somewhere. Yeah. We find the right location for the new element. Yeah. So we can view it as an insertion operation. That's the name of the sort, insertion sort. Yeah. All right, the general case. So we assume the current array with k elements already sorted. Yeah. Now, new element ak, we want to insert it in a currently ordered array. Yeah. How many comparisons do we need? Okay. So the best case, worst case, average case, right? Yeah. Okay. View in that way. Yeah. All right. So add a new element to a currently sorted array and make it sorted. Yeah. So that's the basic step of this sorting algorithm. Yeah. Observation. Insert an element in a sorted array at the right position. So that insertion operation, we need to study that because that's the basic, the main operation of this algorithm, insertion operation. Okay, all right. All right, so now let's study that insertion operation. Shift elements for insertion. Yeah. So in the current array, yeah, so look at this diagram. The current array, these k elements occupy k positions. When we insert a new element, first, we need to find a vacant location for the new element, right? Yeah. Yeah. Just like a hotel, we need to find a room for the new customer, right? Yeah. Here, we need to find a, one location, right place. Yeah. All right. Yeah. After we find the right place, we need to move other elements, right? Yeah. Move other elements, in some way, simple way, then last step, add a new element to that right vacant location. Insertion, to get a whole array sorted. Yeah. So that's the basic. Yeah. All right. So let's do that detailed work here. Yeah. All right. First, yeah, look at this place. Yeah. This place, first, yeah, because the element in this location, original location, that one, in general, it's not in place. In general, it's not in place. So we need to put it in place. Yeah. So this element not in place. We need to put it in place. Yeah. All right. How do we put it in place? First, we lift it. Okay. Oh, we copy this element to a temporary location. How about that? Yeah. Let's put it in a temporary location. Okay? Yeah. After we lift it in a temporary location, then this location is vacant, right? This location is vacant. So we can move other elements, one of the other elements to this vacant location, right? Yeah. All right. So let's do this. First, we do comparison AK with AK minus 1. If AK minus 1 is greater than AK, then we do the right shift operation. Yeah. Copy AK minus 1 to this vacant location, original AK location. Okay? Yeah. One position to its right. All right? That's the first comparison. Then second comparison, compare AK minus 2 with AK. If AK minus 2 is still greater, then we shift it to its adjacent right position. One position to its right. Okay? Yeah. If not greater, then that means AK minus 1, this location, because after the shift, this location is vacant, right? So we can copy AK to this current vacant location, and so on. All right? Yeah, so let's just keep doing, every time do one comparison. Yeah. If greater than, so if the element in that location, AI plus 1, greater than AK, they copy it to its right adjacent location. All right, but sooner or later, you will hit some element that is less than or equal to AK, right? Yeah. Here, let's assume, so this AI, so this element is less than or equal to AK. Equal, we should stop, okay? Equal, we do not need to move further. Yeah. All right. So here, let's assume we're in this place. We just copy element AI plus 1 to its right adjacent location, and leave this location vacant. All right. Then, another comparison with AI, and we assume, because we need to finish this insertion. We need to complete this insertion, okay? So we assume AK greater or equal to AI. If that's true, then we drop this AK to this current vacant location. How about that? That's the idea of insertion sort. Every time when we need to insert a new element, we do this way. Okay? Then, from first element to the last element, we get a whole array sorted. So you run a for loop. Okay? Here we do not use recursion. We use a for loop. Recursion. If we can avoid recursion, then we want to avoid recursion, right? We can save some memory resource. So this one, we don't want to use recursion. So one student told me there is here. Let me give you some updates of our project 1, programming project 1. You need to implement Horner's rule, right? For when you implement Horner's rule, you do not need to do recursion, right? So you don't need the recursion. You use a for loop. You can implement Horner's rule. But one student had recursive implementation. He tried that. So then he sent me the result. So I think it's a good example. He told me, because remember, that project we need to run evaluate polynomial on very large degree, right? Even 10,000, that large. Very large. Then that student told me got a stack overflow problem, because recursion you need to use stack, right? But you push very big, long, huge array, your stack gets overflow. Your stack gets overflow. So in that situation, we should avoid Horner's rule, using recursive algorithm for Horner's rule. then you will have a stack overflow, right? For loop. So we don't need a stack. We don't need a deep stack. We do not use stack. Yeah. Because the variable, all temporary variable, all the temporary variables, they can be recycled, right? Keep recycling those temporary variables. So you do not use much memory space. Yeah. But stack, you use large amount of memory space. So you may get a stack overflow problem. Okay? Yeah. Yeah. So that's the, something related to, yeah. Here, yeah, we try to avoid recursion. Yeah. So we can save a lot of memories resource. Yeah. All right. Yeah. Number of assignments. Yeah. Here, actually, if you look closely, the operations we are doing here, we do two operations, right? Two types of operation: comparison and assignments. You copy element, you copy one element to its adjacent location, that's assignment operation, okay? So these two different operations you need to use here. Yeah. All right, so the number of assignment operations, we use asymptotic notation, big theta of k. Yeah, yeah, because, yeah, you can treat as the average, yeah, because best case is 1, worst case k, best case 1, average case about 1/2 of the k. Yeah. Yeah. All right. Yeah. Next, 8.2, implementation of insertion sort. Yeah. Actually, we're almost there. Yeah. So we do not have much remaining work to do. Yeah. But let us estimate efficiency. Let us estimate the number of comparisons we need to use. All right. Compare and the shift operation. Yeah, here, so because every comparison, after that, we need to do a shift operation. Yeah. So let's put them together. So compare and the shift operation. Yeah. All right. So here, from this diagram, you can see, yeah, one compare operation, then a shift, one compare, basically, one after another, yeah, yeah, yeah. But the last one, we do not shift AI. Yeah, but we have an assignment. We have assignment, last assignment operation. Yeah. So like this. Yeah. All right. Worst case efficiency, yeah. So you need to compare AK with all the other elements. There are K, from 0 to AK minus 1. Yeah. So, all right. So the worst case, yeah, but you need to look at from beginning to end. You need to complete the insertion sort on that n element array. So we need this many comparisons. One, yeah, starting from second element, 1 comparison, third element, 2, worst case, and so on. Last one, n minus 1. Yeah. Yeah. Then the formula, 1/2 times n times n minus 1. Yeah. So this one, we can write asymptotic notation, big theta of n squared. Yeah. All right, yeah. Yeah. Best case, yeah, best case, then every time when you insert a new element, you have the best case. That's one comparison, okay? Yeah, so every round, every time you insert a new element, one comparison, one, all the way from beginning to end, then you only need to do n minus 1 comparison. So big theta of n, best case. Now that's the conclusion. Yeah. So the main property of this insertion sort, yeah, let us make the conclusion. The worst case, big theta of n squared. Best case, big theta of n. How much is the difference? The difference is very big, right? Yeah. The difference is very big. Yeah. Let's recall our previous two sorts. One selection sort. What is the best case? What is the difference? Difference between the best case and the worst case? Zero. Zero, right? Yeah. For the bubble sort, what's the difference between the best case and the worst case? Bubble sort. Also zero. Also zero. Yeah. Because only one case. Yeah. Best case, worst case, the same. Only one case. Yeah. So those two sorts, the difference between best case was minimum, zero, right? Yeah. Here you can see very large difference. Big theta of n, big theta of n squared. Yeah. Later, we will learn several other sorting algorithms. We can also look at the difference between the best case and the worst case. Yeah. You will see the difference. This insertion sort has the largest difference. Has the largest difference. Other sorts, the difference smaller. Smaller, largest difference. Yeah. All right. That's one property. Okay. Yeah. Prominent property. Yeah. All right. Yeah. But this property is useful, so we can take advantage. Yeah. In some special situation, we may like to take advantage of this property. Yeah. So let me give you that special situation. Yeah. Because this algorithm tells us its best case is very fast. Big theta of n. It is fast. It's linear, right? It's linear, very fast. So its best case is very fast. Okay? That is its main property. Okay? Other algorithm, later, when we learn a few more, you will see their best algorithm is, none of them is as fast as this one, for the best case. Okay? Yeah. All right. All right. Now, we may like, yeah, because this property, in some special situations, we may want to use this property. Yeah. All right. Yeah. The average case, yeah, still big theta of n squared. Yeah. So here I do not elaborate. Yeah. Yeah. Basically 1/2. Okay. Basically you multiply 1/2 to the worst case. Yeah. Approximately 1/4 of n squared. Okay. Yeah. All right. Yeah. Yeah. Actually here. Yeah. All right. Sorry. This place 1/2 of n squared, and in this place about 1/4 of n squared. Okay. Yeah. Average case. Yeah. Yeah. But we want to, apply this property. Yeah. All right. So. Yeah, derive it also very simple. Yeah, all right. Now, in the conclusion, I want to describe a scenario that we can apply that best case property. Yeah. Very fast best case, that property. Yeah. All right. Conclusion. If the given array is almost sorted, here we describe the situation. If your data is not sorted, but almost sorted. If your data has that property, yeah, then you should apply the insertion sort. That would be the fastest. It would be faster than you apply any other sorting algorithm. Almost sorted. Okay? Yeah. Yeah. What do you mean almost sorted? Yeah. What do you mean? Yeah, here, I use this diagram to describe almost sorted. Okay? Suppose this line segment represents the whole array sorted in ascending order, but in some scattered location. Yeah. only some scattered location, okay? A few places in this array, this red circle part, the data not sorted, not ordered. Other than that, all sorted, okay? Yeah. So we want to, recover the order. Yeah. We want to get it sorted. Yeah. In this situation, insertion sort is the best. Yeah. Because if you apply insertion sort, you get approximately big theta of n. Yeah. Approximately big theta. Yeah. All right. So you can imagine in the ordered part, because basically there are two parts. Ordered part, you have 1 times n, right? Yeah. But in some local scattered places, not ordered. So when you fix it, you may use a little more comparisons. Yeah. Then when you take an average, overall, still close to that big theta of n. Yeah. All right. So that's the typical situation. You apply insertion sort. Okay. Yeah. Other than this one, then if just a random, arbitrary given array, then we should not use insertion sort. Because if you use that big theta of n squared, that's not good. Yeah. That's not good. Yeah. Later you will see we have some big theta of n log n. Big theta of n log n. So that's much faster than n squared. Big theta of n squared. Yeah. So for the general arbitrary given array, we will choose one of the big theta of n log n sort. Yeah. All right. Yeah. So that's the conclusion here. Okay. Yeah. All right. Yeah. Next. Yeah. So here we finished the insertion sort. Yeah. So you can see, pretty easy, right? Yeah. Yeah. All right. Next. Yeah. But insertion sort, the idea here, useful, also useful. So next, I want to generalize the insertion sort idea to sort 4-element array and a 5-element array. Sort these two special cases. Partially based on the insertion sort, but not completely, partially. That means we need to modify the insertion sort. We need to modify insertion sort. Yeah. Okay, all right. Yeah. So let me show you the details. Yeah. First, let us sort 4-element array. Do any of you know what is the best solution to sort 4-element array? 3 we know, right? Sorting a 3-element array, 3 comparisons, right? Yeah? We know that. Yeah, 3. For 4-element, sorting 4-element array, do you know what is the best number, the smallest number for the worst case number of comparisons? Some idea? 5. Good. Yeah, you get it. Yeah, you get it. Yeah. All right. 5. Good. Yeah. He said the key idea. Yeah. Yeah. All right. So let me explain it. Yeah. Let me explain it. All right. So first thing, before we start, first I like to give you a formula, yeah, because the question I ask you, yeah, if you know that formula, yeah, what's that formula? Seeding function of log base 2, okay? LG, yeah. Here, I can also write log base of 2 n factorial. Okay, yeah. Yeah. So when you sort an n element array, okay, this number is a lower bound. That means the number of comparison you need to use must be greater or equal to this number. If you can reach this number, that's the best solution. Yeah, because it can never be lower than this one, lower bound. Yeah. Absolute lower bound. Okay? All right. Then you can calculate, let's calculate. Okay? All right. Flow a seeding function log base 2 of 3 factorial. What's that? Okay? 3 factorial, that's 6. Log base 2 of 6 seeding function equals 3. Right? Yeah. Next one. Log base 2 of 4 factorial. What's that? 24, right? Yeah, 24. 24 equals 5, right? Yeah, because greater than 2 to the 4th, 16. Less than 2 to the 5th. So, seeding function, 5. All right. Then, let's calculate. Log base 2 of 5 factorial. $120, right? 120. Okay? Yeah. Power of 2, the closest one, 128, that is 2 to the 7th. Yeah. So it's less than 2 to the 7th. But 2 to the 6th, 64. It's greater than 64. Yeah. So seeding function, it's 7. Okay? All right. So here we have the minimum number of comparisons you can consider, you can try. If you can get this many, that's the optimal solution. If you sort 4-element array with 5 comparisons, that must be optimal. If you can sort 5-element array with 7 comparisons, that must be optimal. Okay? All right, so this is the formula. Yeah. Later, if we have a chance, I will show you how to derive this formula. Okay? How to derive it. Yeah. The method is very interesting. Interesting and powerful. Yeah. Yeah. So I try to find some time to show you how to derive it, this formula. Okay? All right. Now, let us sort a 4-element array. Okay? All right? Yeah. It's pretty simple. Yeah. 4-element array. Yeah. All right. Let's assume these 4 elements, they are x1, x2, x3, x4. Okay, all right. Yeah. So this one, for the first few steps, we can use insertion sort. Yeah. First few steps, just use the insertion sort. Okay, all right. Yeah. First comparison, we compare x1, x2, and we assume x2 is greater. Okay? Yeah. All right. Without loss of generality. All right. Second, insert x3 into ordered array, x1, x2. Okay? Yeah. Into with two comparisons. For the worst case. Okay? Yeah. So now, subtotal equals 1 plus 2 equals 3, right? 3 comparison. Yeah. 3 comparison, we get x1, x2, x3. Yeah. Yeah. For worst case, we get it sorted. Here, I just write it for simplicity. Okay? Yeah. We get the array sorted. Yeah. All right. Then, the last step, when we need to insert, last step, insert x4 into x1, x2, x3. Yeah. Here, we need to modify the insertion sort. Yeah. Here, we should not use our standard insertion step. We should compare with the middle one first, binary search. Here we apply the binary search idea. Compare x4 with x2, the first comparison. Yeah. Then after that, you only need to do one more comparison. Okay? Yeah. Either compare it with x1 or x3. Yeah. So in this way, with 2 more comparisons, to get x4 inserted for the worst case. Okay? 2 more. Yeah. Total 3 plus 2, 5. Yeah. All right? So total 3 plus 2 equals 5. 5 comparisons. That's optimal. That's optimal. Very simple. Okay? Yeah. Yeah. So that's the sorting 4-element array. Okay? And we can claim that nobody can use 4 comparisons to sort 4-element for the worst case, not for the best case. Best case or better case, then it's possible. But worst case, it's impossible. Okay? Yeah. All right. Then, next one. Challenging one. Sort a 5-element array. Yeah. That's a very challenging question. Yeah. All right. Sort a 5-element array. The target 7 comparison. Remember, that's the target. Okay? Yeah. Target 7 comparisons. because that would be the optimal. Yeah, so we try the optimal solution first. Yeah. All right. Let's start. Yeah. Yeah. Very challenging. So if you want to try at home, yeah, you may need to spend many hours. Yeah. Many hours. Yeah. Yeah. Here, I just, yeah, do it. Okay, all right. Yeah. I use diagram to do it. Yeah. So diagram, we do not need to write a lot of sentences. We just draw some diagram. Yeah. Okay, all right. Still, we use x1, x2, x3, x4, and x5 array. Okay, all right. Then, we use the tournament method. Yeah, tournament. Okay. Yeah. First a few comparisons. Let us use the tournament method. Okay. All right. Make them in pairs, then do comparison. All right. The first pair, x1, x2, we pair them and do one comparison and assume x1 is the winner. Okay? All right. Second comparison, x3, x4, second comparison, and x3 is the winner. Okay? Yeah. So first comparison, second comparison. Then, third comparison, yeah, so x3, x1, yeah, we do one comparison and assume x1 is the comparison. Three. Third comparison. Third comparison. Okay? All right. x5, yeah. So we, yeah. So the first three comparisons, we do not touch x5. Yeah. After three comparisons, then we need to look at the information we get so far. Yeah. Because we need to use that information for our remaining comparisons. All right. So after the first three comparisons, I want to draw a diagram to show you the current status, state. Yeah. All right. The current state, x1, the higher means larger, x3, x4. You can see these three elements is in this order. Okay, x3 greater than x1 greater than x3 greater than x4. Okay, yeah. All right. Then another one, x2 is here. x2 less than x1. Okay, yeah. Now x5 is here. We don't know. Where is x5? We don't know. Okay? So we need to do comparison. So the next one, our comparison number 4, we need to use x5 to compare with one of the other 4 elements. Which one you think you should do the comparison? Which one you feel, based on your experience, is the best to do the comparison? Can you explain why x1 you think the best?
Because we know that it's the largest
Yeah.
of all the other.
Yeah, yeah. So after one comparison, you get which one is the largest, right? Yeah. So you can eliminate it. Yeah. So that's one idea. Any other ideas? Yeah. Because you have different views. You have different views. Do you have some other reasonable? You take a different view, reasonable.
Could you also compare with x2?
Can you explain why compare x2?
I mean, it's similar to comparing with x1, but then you'll find out the relationship with x1 is to x, or with x2 is to x5. We know x2 is less than x1. We know x1 is the largest of the ones that we've compared with. So if it's less than x2, we don't know. We don't need to compare it with x1 necessarily in that situation. Remain with one other comparison to
Yeah.
find out where.
Yeah. But if it's a greater than x2, then you need to do a lot of work. Yeah. All right. So this situation, usually you have a better case, worse case. Yeah. Yeah. So usually in this situation, yeah. So there is another good method called adversary argument. Here, let me introduce this adversary argument. Yeah. So from the name, you can see adversary. Yeah. We imagine there is a smart adversary fighting against us. Okay? Yeah. All right. Our goal, we want to work on the worst case, right? Yeah. But how do we get a worst case? We imagine there is an adversary would, try to make our life harder to give us worst case. Okay, all right. Then, when you compare x5 with x2, there are two cases, greater than 2, less than 2. Then, this time, we need to ask our adversary, which one you want to give it to us? Which case, which of the two cases you want to give it to us? The adversary would tell us, I choose x5 greater than x2 to make your life harder. That's the adversary argument. Okay? So we need to worry about x5 greater than x2. We do not worry about x5 less than x2. That's the idea. Okay? Yeah. If you fight against adversary all the way down the road, eventually you will beat the worst case. You will solve the worst case. Okay? Yeah, that's the idea. Yeah. All right, so here. Yeah. That question, can we connect to the previous one, sorting 4-element array? In this situation, can you connect a little bit what we did, sorting 4-element array? Okay? Yeah. Look at, what is the longest chain? What is the longest chain? The chain with elements already ordered, that chain. You can observe longest chain, right? Yeah. x1, x2, that chain is not the longest. Okay? Can we look at this chain, longest ordered chain? How about that? Now, when you do a comparison with the longest chain, which element you want to choose? X3. The one in the middle, binary search. Binary search. Here you can see the binary search, you compare in the middle, then your adversary cannot make a big difference. Yeah, because greater than that, less than that, pretty much the same. So any case your adversary choose, basically the same. Yeah. That's the way you beat your adversary. You always compare one in the middle, yeah, to make a balance the two cases. Yeah, almost the same. Then your adversary cannot make it too bad. Okay, your adversary, choose one of the two, pretty much close. Okay, yeah. So that's the way to fight against the adversary. Okay, yeah. Choose the balanced option. Yeah. All right. Here. Comparison number 4. Compare. Yeah. The fourth comparison. Yeah. The fourth comparison. There are two possible results. Yeah. Good. We have about 15 minutes, so enough to complete it. Yeah. Although it's pretty complicated, but we have plenty of time. Yeah. All right. Yeah. Here, let me use this. Yeah, because I need to use the this is my last slide, so I should not waste too much space. I need to use, in a stingy way. All right. Let me use this space to draw two diagrams corresponding to cases. Yeah. All right. One is x5 greater than x3. Yeah. x5 greater than x3. So it should be, so we keep the original part, x1, x2, x3, x4, x5 is here, greater than x3, okay? Yeah. Another less than x3, okay? Yeah, so I draw this one. x1, x2, x3, x4, x5. Okay? All right. And we need to work on these two cases, case 1 and case 2. All right. For case 1, let's work on case 1 first. When we work on case 1, what is the fifth comparison? Comparison number 5. Think about. Yeah. x1, x5, good. Yeah. So do you feel okay? x1, x5? Yeah. Because after you compare x1, x5, you will extend the longest chain, right? Yeah. You will extend the longest chain. The longest chain has 4 elements. That's good. So try to extend the longest chain. All right. Yeah. So we agree. Yeah. So the fifth comparison between x1 and x5, fifth, extend the longest chain. All right. Yeah. So extend the longest chain. There are 2 subcases, right? Yeah. Here, draw 2 subcases. I.1, x5 greater than x1, x3, x4, and x2, like that, I.1, okay? I.1. There, it's pretty close. Last step, we just want to put x2 in place. Yeah. X2 we already know below x1, right? So we only need to compare with x3 or x4. Currently, we have consumed 5 comparisons, right? 2 more to go, right? Can you use 2 more comparisons to put x2 in place? Yes. Easy, right? Compare with x3 and x4. You can get sorted. Case I.1, number 6, number 7, you can get it sorted. Okay? Yeah, I.1. I.2, yeah, let's look at I.2. Sorry, I.2. Oh. Yeah. All right, I.2. All right. x1 greater, x5 next, x3, x4, x2 here. Now, we want to put x2 in place. How do you do the comparison? You only have 2 comparisons to use. S3, okay? The one in the middle, yeah. So this one, because for sure, so let's draw, okay? Yeah. Number 6. Yeah. Then, last one, yeah, because you only need to do one of the two possible comparison. One there, the seventh. Okay? The seventh. Sorted. All right. Yeah, so that's for case 1. I.1, I.2. All right. Then case 2 actually, yeah, case 2. What is the, let's say, fifth comparison, right? Fifth. We need to do fifth comparison. Okay? Case 2. What do you think? Which comparison you want to do for the fifth comparison? Yes. X4, X5, you extend the longest chain, right? Yeah. You extend the longest chain. Okay? Yeah. All right. So the fifth comparison between X4 and X5. Okay? Yeah. After that, although you have 2, can we use without loss of generality, right? To merge the 2 cases, right? Yeah, because, pretty much symmetric, right? Which one larger, which one smaller, it doesn't matter, right? Yeah. So let us merge those 2 sub-cases. Only look at one, all right? Yeah, without loss of generality. Yeah. So X1, X3, X4, X5, and X2 is here. 2 more, yeah, S4, right? Number 6. Yeah. The last one, yeah, one of the 2, last one. Total 7 comparisons. You get a 5-element array sorted. How about that? And that's the optimal solution. That's the optimal solution. Okay? Yeah. Yeah. Think about how much we can learn here. Okay? How much we can learn here. All right? Yeah. All right. Then, before we finish today, yeah, we still have at least 5 minutes. Yeah. Then, how about sorting 6-element array? Yeah. I do not ask you to sort. Yeah. We just think about it. Okay? Yeah. 6-element array. N equals 6. First, let us use that lower bound formula. Okay? First, let us use ceiling function log base 2 of 6 factorial and look at what is the optimal solution, that number. Okay? All right. 6 factorial. Is it 720? 720? 6 factorial? Yeah. 720 greater than 526, right? Less than 1024, right? Yeah, sorry. Yeah. Yeah, sorry. Yeah, all right. Yeah, 512. All right. Yeah. So that is 2 to the 9th. Oh, sorry, 2 to the 9th. Yeah, less than 2 to the 10th. Yeah. So this number, ceiling function should be 10, right? Yeah. So now, the question, is it possible to use 10 comparisons to sort 6-element array? It's possible, right? 10 comparisons to sort. Yeah. Because, yeah. Can you take first 5 to sort it? first 5 to sort it. X1, X2, X3, X4, X5 to sort it with the 7 comparison, right? We just did it. Sort 5 elements with 7 comparison. Then X6, 3 more. 1, 2, 3. How about that? 3 more. It's optimal, right? Think about that. Yeah. Not hard. Here you can see, after we learn the insertion sort, then we can generalize the idea to solve these hard questions. Are they hard questions? Are they hard questions? Yeah? Yeah. You can challenge your friends. One is sorting 5-element array, another sorting 6-element array. Yeah. I think it will be very hard. For people who do not have our background, yeah, here we have the background, right? Yeah. We have, good background. For people without our background, think about how hard these 2 questions, sorting 5-element array, sorting 6-element array, how hard it is. Yeah. So you can see, now we have the good background. Yeah. We can solve these very hard questions. Okay? Yeah. All right, let me stop right here. Yeah. So we've finished part A.